Here we're told we have two connected boxes of fruit. We've got a box of peaches and a box of apples. The box of peaches, we're told, has a mass of 10 kilograms. And the box of apples has a mass of 20 kilograms. Let's get a color we can actually see. Bad choice. How about black? 20 kilograms. And 10 kilograms. We are asked if we apply a force of 50 newtons to this box and it's sitting on a frictionless surface. What is the tension in the rope joining these two boxes, and what is the acceleration of the system? A really quick way to solve this system is to note that the tension is going to cause the rope to stay the same length, so it's basically rigidly connecting these two bodies. So we have a total mass here of 30 kilograms, and I know I can apply Newton's second law. It says that F net is equal to the mass times the acceleration. In this case, the acceleration will be F net, the external force 50 newtons, divided by 30 kilograms is 1.66 meters per second squared. Going into more detail, we can draw our free body diagrams for each mass. I know that pulling down on M1 is the force of gravity, which is equal to M1g. In this case, that's 10 kilograms times 10 meters per second squared, 100 newtons. Similarly, the force of gravity downward on box 2 is M2g, which here, since it's twice as massive, it has twice the weight, 200 newtons. Nothing too interesting happens in the vertical direction in this case. We have normal forces, which are equal to the weight. Not because of Newton's third law, but because this is supported on a surface and not accelerating. So I know the normal force here is 100 newtons. The normal force here is 200 newtons. Now in the horizontal force, where all the action is happening, I know that I've got my applied force of 50 newtons on the right box, and tension is the force of a string or rope or chain trying not to get longer. Tension is pulling to the left on the apples. That same tension, since it's the same rope, is pulling to the right on the peaches. And here we have initially no friction. So there's no force backward due to friction on either of these things. The whole reason we draw the free body diagrams is so that we can analyze forces in the direction of motion, or in components if the motion is more complicated. So this allows us to read off, where I've highlighted in orange here, the net force on each object. So for box 1, I see that the net force is tension. That's equal to its mass, 10, times its acceleration, a. For the second mass, we have, taking the right to be positive, 50 minus t equals 20a. We could solve these by substitution, elimination, or linear combination. I always like the linear combination method for Newton's laws, because in systems like this, due to Newton's third law, if tension pulls to the right on one object, it'll pull to the left on the other object. So adding these together, that t force will cancel out, and we end up where we were up here, considering the whole system as 1. 50 equals 30a, t minus t is 0. So a is 50 thirtieths, or 5/3, 1.66 meters per second squared to the right. Part B, we're asked to repeat this for a case where the coefficient of kinetic friction between each box and the surface is 0. So mu k here equals 0. That is the ratio of the normal force to the friction force, so I know that there's a friction force backward on this mass. Force of friction here will be mu k times Fn. In this case, mu k is 0.1, and the normal force is 100. 0.1 times 100 gives us a frictional force backward of 10 newtons. Similarly, there'll be a frictional force backward here of 20 newtons. It's interesting to consider, will this cause the tension to be greater, less, or the same as in the first case? Well, we need to look at the equations to see how that plays out. I know for the first mass, I have t now minus 10 newtons. T minus 10 equals ma. Here m is 10 kilograms t minus 10 is 10a. And for the second mass in our system of equations, we have 50 pulling to the right, 50 minus t minus 20 equals 20a, 20 kilograms times a. Again, we can take a linear combination of these, and I see that t minus t is 0. 0 plus 50 is 50. We have 50 minus 30 equals 30a. 30 kilograms times a. 20 equals 30a. So a equals 2/3. Or 0.66 meters per second squared. So not surprisingly, the acceleration is lower if we have to work against friction here. But what about the tension? Let's sub back in and see what the tension is. Here first in the first case, the tension is 10 times the acceleration. So the tension in this first case with no friction is 10 times 1.66. That is 16.7 newtons. And here in the second case, I see that t is equal to 10 plus 10a. So that's 10 plus 10 times 0.66 is 6.7. We know that there's a repeating 6 here, just looking at rounding that to 2 digits. So the tension here is, 16.7 newtons. So we have a reduced acceleration, but in both cases the same tension. The reason this happens is that the frictional force is proportional to the mass of each object, so it's proportional to the inertia of each object, and that means that the tension is unchanged even though the acceleration changes.